Yeah. Not necessarily a normal distribution either, yeah. Yeah, right? It's the null hypothesis distribution. It's a probability distribution based on the idea that the null hypothesis is true. Right? That's where alpha comes from. That area under the curve, that's a null hypothesis distribution. Right? Okay, we assume the null is true, and then we find our results based on the idea that the null is true. Okay? Now, where do I get power and beta from? Which distribution? Yeah. The alternative hypothesis distribution. The alternative hypothesis distribution. And that distribution I set up based on only one particular alternative hypothesis. Right? Remember, in general, your alternative hypothesis has an infinite number of possible values, right? If your alternative is that these two groups are not equal to each other, then there's an infinite number of things that they could be equal to, right? They could be not equal to each other by 2 points or 5 points or 10 points. They could be in different directions, right? There's an infinite number of possibilities. When we're calculating power, we take one of those, one alternative that we're talking about, and calculate power based on that one alternative hypothesis distribution, right? So we're only going to do it with one at a shot, okay? Now, what's the center of that alternative hypothesis distribution? Is it the same as the null? What's the null, for two groups, what is the null hypothesis distribution centered on? What's its middle? Yeah, 0, 0. Okay. So the alternative hypothesis distribution, which they also refer to as a non-central t distribution, a non-central t distribution, what's the center of it? What's the center of that non-central? Yeah, delta. Delta. Another name for the delta was the expected t value. The expected t value, that was delta. So it's the center of that alternative hypothesis distribution. What went into delta? Right? I'm trying to connect the dots for you here so you know what we're doing. What went into delta? How do we find the center of that distribution? What components? There were two major components that went into computation of delta that are major things to look at. Yeah? Effect size was one. What was the other one? And sample size, right? Sample size and effect size. Just to remind ourselves, right? This is delta, right? D was effect size, and N is sample size. So those two things, effect size and sample size, go into delta. What happens as N increases? What happens to delta? Assuming your effect size stays the same, what happens to delta? As N increases, what happens to delta? Delta increases as well. As delta increases, what happens to power? This is important. This is exactly what you got to get in your heads. As delta increases, what happens to power? Power increases too. Yeah, okay? So we have our two distributions, right? This is the center of this distribution is delta. And let's say these are our critical values. So I take the critical value from my null and map it onto my alternative, right? So we're looking at the area under the curve for the alternative. On the left side of this line, what is that? What's on the left side of the line? The area under the curve there. It's a probability. Which probability is it? Yeah. That's beta. Yeah, here's beta. And on the other side? What's on the other side? Power, right? 1 minus beta is power. Okay? If you get the idea of this picture in your head, it'll all be much clearer. Okay? So if I increase delta, what happens to power? Yeah. Yeah. Right? We have, this is our null hypothesis distribution. This is our alternative. We take the critical value from my null, but we map it onto the alternative, because the alternative is where power and beta come from. All right? The center of this null is delta. I mean, this alternative, sorry. The center of this distribution, this alternative distribution, is delta. Is that better? Yeah, okay. So as delta increases, that means it shifts it this way. What happens to power? It shifts the alternative distribution that way. What happens to power? It increases. It increases. All right? So things that make delta bigger increase power. Right? Effect size. If we could change effect size, if we could make effect size bigger, we could make delta bigger. But remember, what is effect size? Anybody remember? How do we get effect size? Some kind of basic idea? How do we get, what is effect size? Yeah. Yeah, good, right? It's the difference between the means divided by the pooled standard deviation. Okay? It's a measure of how far the groups are away from each other. Right? Are they 5 points different? Are they 10 points? Are they, 72 beats per minute different? Like, what are they different? Okay? How far apart they are. But it's a standardized way of looking at it. So I could compare different scales to get some measure, some standard measure of effect size. Okay. Can I usually change what effect size is? Not usually. Not usually. Because effect size is usually really a measure of what's going on. So how do I make that bigger? Well, hang on just a second. But effect size by itself, how would I make effect size bigger? You can't really. Like you might be able to manipulate things, but it might not be especially ethical. Like if I was looking at the difference between your class and the Tuesday-Thursday class, in exam grades, and I wanted to see a big effect, right? So maybe I would not give you as much information as I give them. Yeah, I could make the difference between the classes bigger, but would you appreciate that? I don't think so. All right? So we usually can't play around with effect size. So what's the other component of delta? Sample size. Sample size. Okay? So as I make sample size bigger, I can increase delta and therefore power. Let me get back to effect size for a minute. So effect size, there is a difference between the means, but the denominator is, what is it? It's the pooled standard deviation. That's a measure of variability. Occasionally, we can do things that affect measures of variability, the variability of our scores, the design of an experiment. Sometimes we can do things, not often, but occasionally. But the one that we can really play around with is N, sample size. Okay, I'm trying to think if there's anything else that I wanted to remind us from this. Are there any questions? Any questions on this stuff? Yeah? It has to do with the overlap, but think of it in a simple way, right? The simplest measure of effect size, right, a kind of generic term effect size would be how different are my groups from each other. Okay, let's take this class and the other class. One has an average of 85, one has an average of 80. A 5-point difference is, in theory, just a simple measure of effect size, but in a generic way, okay, not the actual calculation. If I wanted to standardize that in some way, so I would take the difference between those means and divide it by my standard deviation. That tells me, in essence, how many standard deviations apart those means are from each other. Just like when we do z-scores, how many standard deviations above or below the mean something is. So this is how many standard deviations apart these groups are. So you can use it with all sorts of different things. Okay, is that better? Okay. Now, another thing that goes into power, alpha, type 1 error, right? If I take alpha and I move it, right, instead of making it 0.05, I make it 0.01. What happens to power? What happens to power? Again, think back to that picture. Yeah. Yeah, it decreases, right? Because here's my critical value, right? The critical values are based on alpha. So if I move my critical value this way, that way, right? So then I'm changing where this line falls. I'm not moving the distributions apart from each other. I'm just changing that criterion. So then I decrease power. I decrease power. Which is, again, why people often don't necessarily change alpha from 0.05 to 0.01, because as you decrease the rate of a type 1 error, you increase the probability of a type 2 error. That's why it's always a trade-off. It's always a trade-off. Okay? Anything else? Right? You need to understand those relationships there. That's the big thing. For next week's quiz, and I'll talk about it at the end of class, that's really, you need to concentrate on those relationships so that you know, okay, this goes up, this goes down, you know, all of that stuff together. All right. So let's get into today doing the computations. The computations are easy. That's not a big deal at all. And I'll show you how, because we're going to be using tables. He set up some really nice tables in the back of the book. They're based on normal approximations. And it's the simplest way I've ever seen power presented. So it's kind of nice. Okay? We're going to start with the absolute simplest idea and work up. So the first question is, if I have a delta of 2.5, okay? So that's starting like with too much information already. But if I have a delta of 2.5, what's my power? That's the first question. So let's take a look at the back of the book at this table. There are two tables for power in the back. This is A3, I believe. And look what we have here. Across the top are our alpha levels, one-tailed and two-tailed. Right? That's just like the T table. You've seen this before. And then down the side here, this is delta. Down the side, instead of degrees of freedom, which we've had before, that's a delta. What's in the body of the table? Power. Power. So for a delta of 2.5, we would go down here. Let's assume alpha 0.05, two-tailed. That's typical of what we do. So 0.05, two-tailed for a delta of 2.5. So we keep going down. And we see that power is 0.71. 0.71. Doesn't get easier than that, right? By the way, okay, so if power is 0.71, what's the probability of making a type 2 error? .29, right? 0.29. That's beta. Power is 1 minus beta. Type 2 error is beta. Okay, let's extend our example. So that's just looking up in one table, but I've given you delta. What if I don't give you delta? Let's take a look at this first example. Let's say I give you an effect size of 1.47. All right? Again, I'm giving you all this information. We're gonna get back further and further until we don't have so much information. But let's assume we know an effect size of 1.47. By the way, did we talk about small, medium, and large effect size? I think we did. Okay, so what is this? 1.47. That's a really big effect size. It's a really big effect size. Okay? So if we have an effect size of 1.47, and each group has 10 in it, that's what that means. Then we could find delta like this, right? We plug in our numbers, and we find a delta of 3.29. Now, when you look up power and delta on that table, the deltas only go to one decimal place, so you'd have to round this number. If you round this number, what does it become? 3.3, okay? Unlike in hypothesis testing, what was the rule I told you in hypothesis testing? If I didn't have exactly the number, what did you have to do? You had to go lower. When you're doing power, you don't have to do that. Just round the way you normally would round. That's because hypothesis testing is different from finding power. Hypothesis testing, you're actually making a decision whether these two groups are the same or not. Power, you're just getting probabilities of whether you're making an error or not. There's no decision involved, really. Right? So for alpha 0.05, two-tailed, for a delta of, what did we say that was? 3.3? We have a power of 0.91. A power of 0.91. Which means what? What's our beta? 0.09, yeah. Okay? Now, that power is very high. The power is very high. Can anybody see why the power is particularly high? Again, this goes back to these relationships, which I'm trying to hammer into your heads. Yeah. Why is delta high? What's the big component in delta that's making it high? Is it sample size? No, it's the effect size, right? The effect size is really big. So even though you only have 10 people in each group, delta is big. Therefore, your power is big. Okay? And remember something, again, kind of logically. If your effect size is big, right? If your effect size is big, you're saying that the difference between your two groups is a large difference. Well, it's easier to detect that with a hypothesis test if it's larger than if it's smaller. Yeah. We will get to it. I don't know if I mentioned it before, harmonic mean of the ends, but you have to, yeah, these formulas assume, but we'll do an example also. These formulas assume that the ends are equal in your samples, but there's something that we're going to come across, this little formula, if they're not equal, called the harmonic mean of the ends. But if it's not, you can use the harmonic mean. It's not a big deal. It's just a matter of a little computation, and then you stick that in instead. Okay? All right? Other questions on this? Other questions on this? Okay? So we've talked about all of these things, how we manipulate power, sample size, alpha, effect size. The standard deviation, that's in your effect size. Okay? So let us continue with these computations. Some of this I've already said. There's the harmonic mean of the ends down there. Okay? We talked about the relationship between alpha and power. Here's something I didn't mention, though. You have more power for a one-tailed test. Let's draw that for a minute. These are supposed to be right above each other. So if this is two-tailed, and this is one-tailed with the same alpha of 0.05, which is going to have more power? The bottom one, right? One-tailed. Why? Why? What did I do, really? Can you see it? What did I change? What did I shift? I don't know if I shifted it enough for you guys to see it. Yeah. That's right. I moved this critical value more this way. So once I change that criterion, I'm making power larger. That's why people like doing one-tailed tests. Right? It's just that nobody trusts anybody to not test in this side, which would increase the probability of making a type 1 error. So, you know, it's really, some people are not happy with it. But you see, they do it because you have more power. You get more power. Okay, if you have unequal sample sizes, so you use this harmonic mean of the ends, okay? You just take your sample sizes, plug them in there, and then you plug that value wherever there's n when you're trying to find delta. Okay? It's not a big deal. Like I said, we'll do an example. Okay. Now sometimes we have fixed sample sizes, and we have a power, like in our heads, we don't want power to go below a certain amount, right? Like a power of less than 0.7 or less is like not great. It's really not great. So we might have in our heads a particular power that we're dealing with and a sample size that we're dealing with. In that case, what we want to find out is what is the smallest effect size that I need in this study in order to achieve the power that I want. Okay? In this case, instead of solving for delta, I'm just solving for effect size. It's the same formula. It's the same formula, but I've just solved for D instead of delta. Okay? So let's actually do an example of that. Let's say the lowest power I want to have for a particular study is 0.7. Let's see. And let's say that I have, each group has 10 people in it. Okay? So now what do I do? Well, what do I have here? I have 2 divided by what? 10, yeah. So what am I still missing? What do I not have? Delta. Where do I get delta from? I get it from the other table. The other table. Let me show you the other table. It's a real simple table. Okay? I think this one is A4. It got cut off a little when I was making it bigger. All right? So look what we have here. We have alpha on top. Down the side here, we have power. And in the table, what do we have? These are delta values. So the other table was power as a function of delta. This is delta as a function of power, essentially. So what do we have? Well, let's assume alpha 0.05, two-tailed. What power did I want? 0.75, right? So I go and I find the delta here. The delta here is 2.63. No, did I want? No, I wanted 0.7, right? So it's 2.48. 2.48. So my delta here is 2.48. So what I'm saying is, if I want a power of 0.7, minimum 0.7, and I only have 10 people in each group, the effect size, the minimum effect size I need for that kind of power is 1.11. So again, what size is that effect size? Big, right? I'm saying that I need a big effect size if I only have 10 people in each, and I want a power of 0.7. Okay? Questions on that? Questions on any of that, where I got something from, what it means? Okay? Okay, good. We're going to just extend this a little more.
Would that effect size go down if you had more?
Yeah, right? There's always remember this, there's always a trade-off between effect size and sample size. If you increase your sample size, then you don't need as big an effect size. And if you have a really big effect size, you don't need as many subjects. Yeah? Again, it's how far apart these groups are from each other in a standardized way.
So, like, I don't understand, like, if you were to apply that to, like, a real, situation, like an experiment, for example.
Like I said, with these 2 classes, right? These 2 classes, if I have my Monday, Wednesday, my Tuesday, Thursday class, and one gets an average of 80 and the other gets an average of 85, a generic effect size would be 5 points. There's a 5-point difference between them. But if I want to standardize it, I have to divide by the pooled standard deviation. That way, it tells me how many standard deviations they are away from each other.
So if you want to manipulate effect size, like you said that it's not really possible, like would that be?
It's unusual. Yeah. That's why you don't do it. You know, you could increase, like if you're using medication, you might increase the medication and you might get a difference in something. But what medication are you going to increase? You know, if it's something that's good, that might be okay. But, you know, if it's something that has horrendous side effects, you're not going to do that. You know? So changing effect size is dicey. I don't want to say you can never do it, but it's unusual. Okay? Good? All right. Now here's the million-dollar question that people always want to know. People often ask, what is the power for a particular study? But sometimes you ask that after the fact, right? I've done a study, and I've gotten whatever results. I haven't gotten significant results, let's say. And then somebody says, okay, but what was the power of your study, right? Because that could help you figure out what's going on. But very often, the question is the other way around. Before you're doing a study, and you want to know, how many subjects do I need to attain a particular power? To have a good shot at rejecting the null, how many subjects do I need? In that case, we're not solving for delta, we're not solving for d, we're solving for n. Same formula, but we're just solving for n here. So, and this will give me my sample size. So let's do an example of that. Let's say I want a power of 0.75. Okay? And let us assume that we're going to use the effect size that we just got from the last example. Okay? So we're just going to use this effect size. Okay? So what am I missing? What's the only thing I'm going to be missing here? Yeah, it's still delta. All right? So I need to find delta for a power of 0.75. And again, we'll assume alpha 0.05, two-tailed. So then the delta is 2.63. Just gotten from the table, 2.63. Our effect size is 1.11. Don't forget to square it. And this gives us this. So what does that mean? What is that? Yeah. No, I said for this study I want it to be 0.75. Not because of that. I just said let's use the effect size I got before. This is made up numbers, okay? Right? It's just I'm taking each little example here separately. So before I said I have 10 subjects in each and I want a power of 0.7. Now I'm saying, okay, I want a power of 0.75. And for this example, let's say I have an effect size of 1.11. Okay, is that clear? Is that better? Okay. All right? Yeah. Yeah, right? You don't have 11.23 people, so it's 12. 12 per group. 12 per group. You have to understand that. Make sure you have that down. 12 per group. Yeah?
So this only really works when the sample sizes aren't that.
What do you mean?
Well, because you need 12 per group, so it means the sample size for both groups.
Well, no, I mean, so that's, again, it's like minimum 12 per group. So if I have 12 and then I find 14 somewhere, I'm not going to tell those other two people they can't be in the study. Do you know what I mean? It's just kind of a minimum value. Yeah. Okay, so where do we get how much power is enough? Two questions. How much power is enough and effect size? Okay, so let's do power first. What did I say was kind of a minimum power? The truth is 0.8 is really a minimum power. You might play around with 0.7 or 0.75, but really, because what that means is if you have a power of 0.75, what's your type 2 error rate? 0.25. You're willing to accept making a type 2 error with a probability of 0.25. That's high. That's high, but it's typical. Okay? But you don't want to go lower than that. All right? Now, this is not to say that on some kind of homework example or an exam example, they might not say assume a power of 0.4 or something like that. But as a researcher, you wouldn't want that, okay? The other thing is, where do I get effect size from? This, I just made up, right? I just said, okay, this is my effect size. But where do I get effect size from? We talked about this last time, a couple of options. Where do I get effect size from? Yeah. Yeah, sometimes you actually have D based on previous research. Sometimes you don't have D, but you use, what do you use to estimate it? G, right? Sometimes G is gotten from, maybe there was one study in the literature you took their sample statistics from, right? Maybe you've done a pilot study and you've taken your sample statistics from that to figure it out. If you don't have any of those, what do you use? You don't have any of those options for effect size. What do you use? Anybody remember? Cohen's guidelines. Cohen's guidelines, 0.2, 0.5, 0.8. Right? You're doing new research. You don't have an effect size measure, but you want to estimate either what your power is going to be or your sample size or whatever. So you can take those guidelines. But don't get too ambitious, you know? Don't use 0.8 if you really think it's going to be a small effect size, because it's not going to give you usable information. Okay? All right. Now, one thing you could do is you could set limits on sample size, which is essentially all it is doing 2 more sample size examples. But you're just setting kind of a range for yourself as to how many subjects. So let's actually do that, just so you can see what I'm talking about. So setting these limits is based on your effect sizes, if you have small or large effect sizes. So let's assume, again, let's say I want a power of 0.75. I want a power of 0.75, and I'm solving for the number of subjects I need here still. So I want a power of 0.75, and I want to find the largest number of subjects I'm going to need. So that's with the smallest effect size possible. So what's a small effect size for Cohen? 0.2. Not that I want to solve for a large one, but it's kind of like, assuming I have a small effect size, how many subjects do I need? That's kind of a better way of asking the question. Assuming I have a small effect size, how many subjects do I need? Okay? Where do I get delta from? You have a table. Right? We actually have this one, right? 2.63. Because it's the same as the power we used before. Take a look at that. Yeah, you're reading that number right. How many subjects do I need? 346 in each group. Why? Because I have a tiny effect size. Tiny effect size. Okay? Now, what if I was able to assume, so I'm looking there, it's like, wow, I have this tiny effect size. I'm going to need that many people. Maybe I'll have a bigger effect size. Let's assume I have a big effect size. So what's the only thing that's going to change then? Is delta going to change? I'm solving for the same power. So that's going to stay the same. What's the only thing that's changing? Here, right? Let's try it with a D of 0.8. A little bit of a difference, eh? That's because we made effect size that much bigger. Generally, if you're doing a study and you're trying to estimate this stuff, you're not going to have a big effect size. I mean, I can't tell what kind of work you're going to be doing, but in psychology in particular, I think mostly we have more moderate effect sizes. Yeah?
Okay, I want to see if
Sure.
So basically, it says that you need 346 people per group
Yeah.
in order to say that their differences are significant?
No, 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 no. You need that many people to get that high a power, okay? Remember what power is, right? Power is a probability. It's a probability of saying these groups are different when they really are. So all I'm doing is increasing those chances, right? Because the groups could be different, right? The groups could be different. But if my power is lousy because either the effect size is small or I don't have very many subjects, I'm not going to say they're significantly different. That's not how it's going to play out. This just ups the possibility. Yeah?
What's the second and result? I can't tell if
Oh, 21.62. Or 22 people. Okay? Now I'm just going to mention this because I don't think you're going to have any examples with it. You won't have it on the test, but you should just have some idea. The power of a one-sample test, right? We've been talking about two samples or two groups now. A one-sample test, take a look at this formula for delta. What's different from two groups? We dropped the 2, right? So the power is larger for a one-sample test. The reason it's larger is because there's less variability. If you have two groups, they could be much more different from each other than one group is from a central mean. So because there's more variability with two groups or less variability with one group, you tend to have higher power. Okay? That's all I wanted to point out. Like I said, there might be a homework example with this, which you could figure out that the computations are the same. But I just wanted you to hear that basic idea. It won't be on the exam. All right, let's do some examples. I think I want to give you a clean page here. Okay. Now this is starting back further. My toes are getting numb. I just can't imagine what it's like for you guys. You're not moving. Okay, those numbers, those means, it's the mean number of minutes it takes people to make dinner with children and people without children. Okay? So the question is, I'd like to find out the power of this study. And I have no other information than this. So how do I go about doing this? Well, first of all, so I want to find power, all right? So what are the steps leading up to that? Before I find power, what do I have to find? Yeah. Effect size. Why do I need to find effect size? Because what's the step after I find effect size? Yeah, delta, right? I need delta to find power. I need effect size to find delta. So we're going to find effect size. What's it going to be? Is it going to be D or G here? G, right? Because I have my sample statistics. Unfortunately, what's the problem? What do I not have? Yeah, I don't have the pooled standard deviation. So you have to find that. So we'll find the pooled variance and take the square root. right? But that's the pooled variance. We need the square root of it. Anybody not sure where something's coming from? Okay, so that's my pooled variance. So now I can go back and I can calculate my effect size. Because look, I mean, there seems to be a big difference between these two groups. But if there's a lot of variability, it's really hard to tell. Now, he doesn't put it in, but really you can think of this as absolute value, right? Especially for effect size. You don't have to worry about that it's negative. So that's my effect size for this study. So again, yeah? No, I subtracted the one here, right? It's n1 minus 1? Yeah. Okay. So my effect size, I have a large effect size, right? I have a large effect size. So now what, yeah? Because it's n1 minus 1 and n2 minus 1. Okay. So now what do I need, right? I have my effect size. Got to find delta, right? Got to find delta. Again, he doesn't write the formula with G. He writes it with D, but I want you to remember that you can, it's either way. So question, what is N? Yeah, 5. All right. How do I find power? Where do I get power from? The table. So what's my delta? Remember, it rounds to only one decimal place, so what's delta? 2.2, yeah. So 2.2. 0.05, two-tailed, 2.2. Our power is only 0.6. It's only 0.6. Why is it so low with such a big effect size? Yeah. Yeah, our sample size is really, really small. I know. It's like frostbite if you put up one finger. Okay? All right? Are you all cool with this particular setup? Because I want to ask another question then. All right? Okay, so here's another question. If you wanted the power to be 0.85, okay? Let's say instead of a power of 0.6, I'm saying, oh, wow, 0.6 is not good. I want a power of 0.85. Then what I'm doing is, so how many subjects do I need to get a power of 0.85? Okay, so in that case, I'm solving for n. And I get my delta from that other table. Right, what is power 0.85? So a power of 0.85, again, alpha 0.05, two-tailed. Our delta is 3.0. 3.0, that's high. And the effect size, I'm using the effect size that I just used from my study. Yeah. Yeah. You're doing it based on what you have. because you have no other information, right? But yeah, it's possible that the effect size might change also. Again, we're just talking about probabilities, really, you know? Okay, so what does that mean? How many subjects did we really need for the study, for bigger power? Yeah, 10 per group, 10 per group. Okay, I have one more question on this. What if I did the t-test for this? Okay, let's say I did the t-test for this. I'm going to do it really quickly because I just want you to see something, all right? It's just a t-test. They're equal sample sizes, so the pooled variance t-test for equal sample sizes. Again, our n is 5. Okay, that's my t. So what do I need to do to find significance? Slow down so you can write? Yeah, okay. Yeah, I have to find the critical value, right? I need a t-critical value. So I need the degrees of freedom. What are the degrees of freedom for this study? Yeah, to remind you, right? They're 8. 5 plus 5 minus 2. Or take off a degree of freedom for each group. So the t-critical value, if I look that up, which I'm just going to tell you, is plus and minus 2.306. All right. What would I be doing here? Yeah. We failed to reject the null. We failed to reject the null. But, right, we failed to reject the null, okay? But we had a really big effect size. So why did we fail to reject? Probably because our sample size was so small. Even though our effect size was large, we had low power, right? The probability of rejecting when it's really false was only 0.6. So we had really not good power for this study. Now there's a couple things involved. One is the sample size, but the other is the variability. There's actually quite a lot of variability in the amount of the numbers of minutes it took to make dinner. There's a lot of variability. Okay? Questions? Questions on any of this? All right, I want to do one more question that to show you the harmonic mean of the ends. Okay? Actually, we can do it on this, so never mind. So what I'm going to do is, you remember the study where we looked at boys and girls and extroversion for Chapter 7? So let's calculate the effect size and find the power for that study. Now, the problem was, for that study, and you remember, right, there were like 49 boys and 63 girls, something like that. So, yeah, 64. So we have to find the harmonic mean of the ends. Because our sample sizes weren't the same. Okay, because I am going to need that harmonic mean of the ends. So one thing I'm going to find now is, what do I need to find power? for that study? What things do I need to find? Yeah, effect size and delta. So let's find effect size. This number I'm putting underneath here, I'm not going to calculate it again. You're going to have to go back and do it yourselves if you want to figure out where it's from, which is not a bad exercise. Okay? Because if you remember, for this example, we didn't do a pooled variances t-test. We actually did a separate variances t-test. But let's say if you went back and you calculated the pooled variance and you got the square root of it, it would be that number. So you could go back and calculate it if you want the practice. So what did we have here? That effect size. What do we have here? The size of the effect size. It wasn't so big, right? 0.2, 0.5, 0.8. So this was not even really a medium effect size, although getting up there. Okay. So now we have to find delta. So here, my n is going to be the harmonic mean of my n's. This is where you replace it. Okay. So then where do I get power from? I have delta. Where do I get power from? The table. So if I look it up on the table, I guess I'll show you guys, although I think you can do it at this point. For a delta of what? 2.3. My power is 0.63. 0.63. Again, not overwhelming here. Okay. And if you wanted to find out, I think I'm just going to give you the answer, and you go figure it out. If I wanted a power of 0.8, if I wanted a power of 0.8, how many subjects would I need? Okay. I'm going to tell you what it is. It's 80.99 or 81 subjects per group. But you could go back and do the computations if you want. I don't really want to keep you in this room longer than is absolutely necessary. And I want to talk about a couple things first. Okay? All right, questions? Questions on any of this? This is all I'm going to be talking about for power, so I just want to make sure that you have this down. Okay, so the last things I want to talk about your exam, but I also want to talk to you about research opportunities. And I'm just going to write down the website address. All right. There are various research opportunities. Sorry, there are various research opportunities at NYU. You know, it's a really good research institution. So we just wanted to make the announcements. There is the Dean's Undergraduate Research Fund, where you can get some money to do research at NYU. So if anybody's interested in that, I believe that website has everything, but I also have some stuff up here if you're interested. There's an undergraduate research conference in April where you can present things, and that always looks great, and it's a good opportunity. For any of you who want to do research at all in any way, shape, or form, whether it's for graduate school or med school or just because you're interested in it, these are really good opportunities to do it. And Yeah, that's pretty much what I wanted to say. The abstracts of students who participate have it published in a book called Inquiry. So that's for that. Okay, why don't I tell you about your quiz next week? Okay, so it is chapters 5 through 8. Yeah, I couldn't bring myself to start correlation today. It was just, all right, so here are the multiple choice questions. Conclusions about null hypothesis testing. The relationship between z-scores and p-values. How to reduce type 1 errors. Type 1 and type 2 errors. Confidence intervals. Critical values for confidence intervals. All right, the relationships between t, variance, power, effect size, and sample size. T, variance, power, effect size, and sample size. And what goes into them. Right? All the things I ask you. One-tailed versus a two-tailed test. Bless you. And pooled variance. Okay. Now computations. Let me just tell you what they are, and then I'll go into the detail. You're going to have a one-sample test, a two-sample test, and a power question. All right? One comment, folks. When you do this, start with your computations first. Okay, they're worth more. It's a long quiz, and you need to get them down. You need to come in and do this. You need to know what you're doing. You can't come in and start thinking, power, effect size. You have to be able to hit it running. Okay, I'm telling you this now. All right, so for the computations, a one-sample test, hypotheses, things you're going to have to give me for it. Hypotheses and symbols. Standard error of the mean. Confidence interval and test. Interpretation of the results and the interval. And the decision you make. You don't have to do APA for this. Yeah, that was your question? For that question, you don't need APA, okay? The two-sample test. Hypotheses in words and symbols. Words and symbols. Standard error of the difference between the means. And again, remember, you could be given variance or standard deviation or sum of squares. You need to be able to get it from any of those. Okay? Confidence interval, and you have to know, and the test, t-test. You have to know which t-test to do. Interpretation of the results and the interval. Decision making. And APA format for this one. Yeah. Which part? Standard error of the difference between the means? Okay, confidence interval and test. Interpretation of results and interval. Decision making. And APA format. Is that good? Yeah. Yeah. Interpretation of the interval means I am 95% confident that, as opposed to reject or fail to reject, right? Those are two different questions. And the last question and the last computation question will be power, just like we've done here. Right? You're going to have to calculate effect size, delta, n, and power. Just like you've done in lab and just like you're doing here. Yeah? Yeah, I posted them this morning, actually. Yeah, yeah.
When writing the interpretation results, should we just write that first person like I am 93%?
Yeah. That's fine. That's fine. Okay. Questions? Other questions? Yeah. Power, effect size, delta, n, and power. All right? Okay, folks, go get somewhere warm.